Hello everyone, once again another video from Pathfinder Tuition. So today is back to chemistry. So on an alternate week basis, right, like 1 week I will do physics, 1 week I will do chemistry, which means to say that if you are looking forward to any content related to chemistry, usually it's alternate week lah. So this week I will be doing chemistry, so next week I'm going back to physics again. Okay, and in today's lesson, we're going to talk about one of the things that is, I think one of the skill set that is more useful for you. So in the last lesson, we talked about mole concept and stoichiometry. Okay, I did not completely talk about every single aspect yet, but it's just to give you an idea of how to go about doing it. And in today's lesson, we're going to talk about this topic called chemical energetics. For the combined science students, this is really just an, don't need to do much calculation, or rather zero calculation. Mainly it's just to get you to understand the idea of what happens if, let's say, energy is released, what happens when energy is absorbed, so on and so forth, and how the different compounds can have different amount of energy released and as well. But it's very qualitative, not so much quantitative. But for the pure science student, when you learn this topic, you find that you have a lot more calculation to do. So which is why today's lesson we are going to explore that. And toward the last part, I think which you will be most interested in is to look at how we can actually calculate with actual quantity given. So this topic actually is linked to the mole concept topic. For the secondary student who have not learned this yet, I think it will also be a good exposure. So eventually when you learn in school, right, you will be able to better understand exactly how the mole concept topic will be linked to this. Okay, so let's get started. So the first thing that you learn in chemical energetic is talking about bond breaking and bond making. And for any chemical equation, right, you will have the left side, right side, what we call the reactant. Okay, let me try to write it. Reactant. And then it will lead to the product. So any student that have been learning chemistry up to this point, you should be already able to understand, okay, reactants and product. And at the end of the day, we don't just stop there and saying that it happens. We want to know whether it can happen. We want to know when it happens, what will be the consequence. So that's the thing that we will be looking at. And in today's lesson, we're going to focus on the idea of bond breaking and bond making. And bond breaking is, as the name implies, you want to pull the bonds apart. If let's say you have a, for example, H2O, you know H2O, right? So let's say we have one H here, and one H here, and one O here, right? So in the case of a structural formula, we will normally show the lines that's connecting between the atoms itself. And this is important because we want to know what kind of bond are we looking at. Is it a single bond? Is it a double bond? Is it a triple bond? So on and so forth. And what is connected between what? So all this must be very clear. And bond breaking is talking about the energy needed to take a scissors and cut it so that they can be separated. Okay, and of course, why do you need to do that? Because after which, the next step will be to talk about the bond formation. So when the bonds are being formed, you are basically like a Lego piece, you try to snap them together. Okay, and when that happens, it's the reverse of bond breaking. So if I'm breaking the bond, I put in energy. So on the reverse side, if let's say I'm going to put them back together, then the energy that you have in extra will be released to the environment. Yeah. So which is the reason why, right, most of the time, if let's say we have a lot more bond breaking as compared to bond making, right, you need to get the energy from somewhere, isn't it? So let's say I have this. This is the reactant. Let's call it R. If let's say you need the energy that you need, right, basically the energy must come from the everywhere else. So this is the reason why in the case of an overall bond breaking process, this will always cause you to absorb heat from the surrounding. So one of the telltale signs that this is happening, overall absorption process, right, is because that you will see that the temperature of the surrounding will start to fall. Because when energy is being passed to you, I have less energy, then that will affect the temperature directly. Okay, so this is actually one of the things that will happen. Overall, a bond breaking process. But if overall is a bond making process of forming, then on the other hand, right, you will see the opposite happening. So the reactant, or rather at the end when the product is formed, right, the arrow will be pointing outwards instead. Of course, this is a net. That means to say the resultant. the in minus the out minus the in. So the blue one, right, overall will be for the case of an overall energy release process or bond making process. Because at the end of the day, right, you need to pull them apart first, rearrange before you put them back together, like how you play Lego. You cannot ask me to form another shape without pulling them apart first. So this idea will not be different in the case of chemical reaction as well. Right? So as I mentioned just now, Lego. You want to pull them apart first into individual pieces before you can put them back together into other shapes. So the thing is that, right, you cannot just do one without doing the other. That's why in all chemical reactions, it's about breaking them apart first and putting them together. And the energy that you need to do so basically will be different. Like if you're talking about pulling different bonds apart, they have different what we call bond energy. So meaning to say it's related to how strong they are. Then after that, the energy that you need to put in will be different. Okay, and just now as I mentioned, you can be taking the energy from the surrounding, or you can also be taking energy, giving energy to the surrounding. So in chemistry, we call it endothermic or exothermic. So endothermic is talking about overall, you're taking energy from the everywhere else because the energy requirement to break the bond is a lot more. You have a lot more energy that you need to take in versus the energy that you can release back after the bond is formed. So this is a net process or the difference. So total energy taken in, if it's more than the total energy released, endo. Then total energy taken in is less than total energy released, then this exo. That means say you release the energy. Okay, so this is the word that we must remember from here on. And of course, at the end of the day, as chemists, when we look at the reaction, we will look at it. I don't necessarily need to go down to the parts of it. I can also look at the entire overall picture. So we use the energy profile diagram, one of the diagrams you will use to help you to make sense of it. Many students make mistake here, so please take note, listen. So this mistake I'm talking about is when you mark on the diagram, okay, the energy absorbed or released, the overall change in the energy rate should always be from the reactant to the product. Okay, this is a product, this is a reactant. So the difference is the energy released or energy absorbed. So quite commonly, people will make a mistake by giving this as the answer, the energy released and absorbed, but this is not. This last one that I draw, this is called the activation energy. For those who have already went through this topic, you will remember that activation energy is the energy you need in order to overcome the barrier for the reaction to happen. So the minimum, right? And this is the thing that catalysts can bring it down. So if you have catalyst, this will be lower, easier for the reaction to happen. So it's more likely that you have the reaction and the rate of reaction will increase, become faster. Okay, so the activation energy. So this is actually not the energy release. The energy release or the energy absorbed, you should compare the reactant and also the product. So by that, you're looking at the energy that the reactant and product have, right? So that's actually what you're doing, you're comparing. Overall, if my energy at the end is higher, then I should have taken in energy. If overall the end part, the energy is lower, then you should have given up some energy. So the right side is the one where you give up energy because the end point is here, right? This is the product, this is the reactant. So you actually have less energy at the end. Okay, and then coming to the next part, you talk about breaking and forming. Can we have a number to look at it to decide whether this is an overall absorption or release? So we look at this thing called the bond energy. So bond energy is usually a table that will be given to you, but your job is to figure out from the diagram exactly are we looking at which bond. So it could be a single bond, could be a double bond, but briefly you can see that if let's say you have more bond, obviously, right, you got more strings tied to each other, then you need to break them, you need more energy, more effort. So this is the reason why overall multiple bond usually will cause there to be more energy that to be released or taken in to break it as well. So single bond is easier, and take note that this is not the energy that they have. Okay, I have students telling me that they add up all the bond energy, then they say this is the energy that the substance have. No. This is the energy you need to take in to break it, the tie needed, but it's not what they have. And this is the energy you need to, give out if let's say you are forming this bond. But this is to account for the difference, not so much of accounting for the energy that they have. But we can use this difference to help us to understand they are overall taking more energy than the one I give out. So that we can do. But we cannot say that this is the energy of the substance. So remember, bond energy is not the total enthalpy, which is the word we use for energy here, of the substance. But this one can help you to account for the difference or the change in the enthalpy. Okay, so you want to talk about overall did I gain or lose? Okay, you can look at the bond energy, because taking energy to give out energy when you make, so in this case, when you take in more than you give out, then overall you have gained energy. So you have an enthalpy that's increased, not decreased. But we don't use bond energy to look at the total energy they have. This is not true. Okay, this is actually not true. So if you want to calculate the enthalpy change, usually we look at this as a change in H, triangle H. Then this will be total energy absorbed minus total energy released. But in my opinion, if you don't follow this simple rule of absorb minus release, you want release minus absorb, so long as you understand and you give the correct sign. Okay, this really is to help you to give the correct sign. Because from here, if I get a negative, okay, a negative here actually means energy release. Because I can only get a negative when I release more than I absorb based on my calculation. Then from here, positive is energy absorbed. So the convenience of learning about this formula and calculating in this manner is really to help you to decide when you get a negative energy or is it release, when you get a positive energy or is it absorbed. So quite quickly you can determine that. So once again, you can immediately say this is endothermic or this is exothermic and so on. So the benefit of having this sign is actually, this calculation is actually this. But if let's say you understood the thing and you are able to manipulate the equation to calculate otherwise, I think it's possible. However, you will then need to realign your idea of what is positive, what is negative. So because of that complication, right, so all students, please try to follow this absorb minus release to get the difference. Okay, and of course the last part of the video, let's take a look at how to make the calculation now. So in terms of the bond energy. So a typical equation given to you will look like this, where the next question they will ask you will be, right, what is the enthalpy change for this reaction? In some questions, they can also give you the enthalpy change and then after that ask you to calculate a different thing altogether by giving you the quantity of the thing they have, and then they ask you how much change in energy will you get in all. Okay, so let's look at this question. So this question wanted to know what is the enthalpy change. Is it the exothermic? Is it endothermic? Do you release more or do you gain more? Okay, so first step you need to do, I always will do that. I will try to draw out the structure formula if it's not clear to me. So C2H2, right? Possibly we can draw out the formula like that. So 2C, okay, then one H here and another H here. So C2H2. So what happens is that, right, with this then it's very clear what kind of bond is involved. It's unlikely that the C don't bond together, it's just the C and the H. So definitely the C will be bonded together, and then after which, right, you will have two H's over there. So this is my first diagram. But you think about it, right, actually for the case of this C2H2, it is possible that there could be a double bond, because not forgetting that every C can actually have up to a maximum of 4 bonds. So now only 2 is being used to bond to these H's. So which means to say that, right, I have a remaining 3 bonds each. In fact, I suppose that this should be a triple bond. So double or triple. So total 4, right, I only use 1. So the remaining 3 should be, they bond together. So triple bond. And you can see, you have 1, 2, 3, right? Single bond, double bond, and triple bond. So this should be a triple bond as a result of that. Right? So you got 3 more spare bonds, right? They will bond with each other. Then the H's only need 1. Okay, and why 1? Because hydrogen just need 1 more electron to get a maximum of 2, so the bond is stable. Okay, coming to the next part, so the H's themselves, okay, so plus H, okay, I draw the structure formula. Then at the end of the day, right, I'll have C2H6, 2, 3, 4, 5, 6. Okay, something like that, C2H6. So knowing how to draw the structural formula seems to be very important. Then you will be able to use the correct bond energy. Okay, so what is the enthalpy change? We look at the left side. So left side is breaking. Breaking means take in. Right side is forming. Forming means give out. Okay, so right side is form, left side is break. So now if we look at this, we can see that, okay, the energy that we need to break it, this is per mole, right, per reaction. So I have one triple bond, so I'll put 839, so this is absorbed, right? 839 plus what? I got 2 CH bond, so I will plus 2 times 413. This is the total energy taken in. Then on the right side, if I'm actually forming, I'm releasing the energy, I will count how many CH bond I have. I have 1, 2, 3, 4, 5, 6. And this is a single bond because I already have 3 more H's bonded to me. I cannot bond with the carbon with a triple bond or double bond. So this is a single bond. So I will then have to minus away 6 times 413. And then I have to minus away the C single bond 347. Okay, and then after which, okay, let me transfer this to the bottom. Okay, let me rewrite this again. A bit too long already. Okay, let me do it again. So it's, as I mentioned, 839 plus, okay, the left side is 2 CH bond. So 2 times 413. Then minus away 6 times 413. Minus away the C single bond 347. Okay, like that. So let me press in my calculator and see what this will get me. 839 plus 2 times 413 minus 6 times 413 minus 347. So you get negative 1160 kilojoules per mole. So take note that this calculation is for every 1 mole of the substance per mole. Yeah, okay, so this is the enthalpy change for this reaction. And now if you look at it, right, because it's negative, this is overall a exo. Okay, this is means exothermic. Why? Because negative means overall you give out more energy than you take in. Okay, you give out more than you take in. So this is overall exothermic. If let's say you get a positive number, then it's overall endothermic. But whether it's positive or negative and what does it mean, it really depends on are you following the formula. So if you are taking the absorb minus away the release, then you can just take it as positive is going to be endo, negative will be exo. Okay, you can do that. Alright, for the last part of the video, let's have a look at the next question. Okay, the next question, which is this. So now instead of asking you to calculate the enthalpy change, I don't give you the bond energy, but now I ask you what would the energy release from this. So you already know it's energy release because the enthalpy change is negative 2400. And let's work by proportion now, because in this question they gave you 0.24 gram. And remember in chemistry, in the last video I mentioned, I said that to work by proportion we use mole, not mass, not volume. Okay, let's use mole now. So 0.24 gram. So what will be this? I first find the number of mole first. So 0.24 divided by 24. How do I know 24? Okay, because 24 is the mass of mg. For 1 mole of mg is 24 gram. So I'm trying to find out how many mole is 0.24 if I'm going to use that to react with excess oxygen. And based on my previous video, you recall that if oxygen is excess, that means to say you have more than enough. Then the limiting reagent is the one that determines what is the final amount of energy release. So you take 0.24 divided by 24, you will get 0.01 mole in total. This is the amount of magnesium that you have. Okay, and in this reaction, you need 2 parts of this, right? So every 2 mole of Mg needs 1 mole of this to give you 2 mole of this. So because of that, right, in order to calculate the per mole one, right, okay, this is the total you have. This is the total, right? So you want to calculate the per mole one, remember to take 0.01 divided by 2 first, because this is actually for this every 2 mole of Mg. So every 1 mole is 2400. So in this case, I'm going to work by proportion now. I take this 0.01 divided by 2 multiplied by 2400. Okay, this is in kilojoules. Huh? So I divide by 2 multiplied by 2400. I'm going to get a negative 12 kilojoules. Okay, so the part of dividing by 2 is extremely important. So to make it simple for you, you calculate what you have first, and you look at the recipe, the chemical equation. If let's say there's 2 in front, you divide by 2. If there's 3 in front, you divide by 3. Before, you work by proportion multiplied by the actual enthalpy change in these questions. Okay, so minus 12 joules, it means to say that if you only got 0.24 gram, we are not supposed that we can get the full negative 2400 kilojoules because it's only 0.01 mole. Okay, it's not 1 mole. So 1 mole, then you get 2400. This is much less. Okay, so that's all for this video on enthalpy change. So I walked through with you to discuss about what is the difference between endo and exothermic reaction. I talked about the concept of bond breaking and bond forming. And of course, I showed you 2 examples. One where you use the bond energy to calculate and decide whether what is the overall enthalpy change. Then you will know whether it's exo or endo. And of course, the last part, we work on to talking about the proportion. Okay, if I give you this much, then do I suppose that we can get 2400, which is for 1 mole. So you might not have 1 mole. So the point is always remember to calculate the number of mole you have based on the quantity. Okay, so it could also be volume as well. I can also use volume to calculate. So volume would have been, right, I will have to take the actual volume divided by 24 dm cube or 24 cm cube, depending on what is your unit for the actual volume. Then you calculate the mole already. Once again, the second step is the same. If there's a 2 in front, the coefficient of your Mg, you divide by 2. If there's a 3, you divide by 3 before you multiply to the actual energy per mole. Okay, so that's all for today's lesson. We will move on to the next part to talk more complicated concept, but I will focus on the skill set that you need in order to accomplish the paper. So skill set that you need for chemistry is namely talking about topic like this, mole concept, okay, how to understand your chemical calculation, how to write chemical equations. These are the things that I will focus on. So I might not necessarily go through every single topic, but if let's say you want to request for a certain topic, please feel free to comment and then or email us. You can get the email from our website and contact us, then we will try to get back to you as soon as possible. Okay, so that's all for today. Hope you liked the video. Help us to share and subscribe to the video. And of course, main thing is that so long as you like our video, we will definitely be more motivated to continue to have more content for everybody. Okay, I will see you again in the next video. Thank you.